Okay, this is the second video on inverse trig. In the first video, we talked about inverse sine, cosine, and tangent, and now we're going to start off by talking about inverse cosecant, inverse secant, and inverse cotangent. So the first graph here is the graph of cosecant of x, and originally, or looking at this graph, the domain is all reals except every k pi. And the range is negative infinity, -1 inclusive, 1 to infinity. Now, again, just like the other graphs we've done so far, clearly this isn't 1 to 1. So thinking about how to restrict it, so I've got a consecutive interval, or consecutive intervals if need be. You're going to find in this case we're going to have to separate it a little bit in terms of it's just not going to be defined over one full interval, and capturing all the ratios. So the convention for cosecant was to keep it the same as inverse sine. So either a positive quadrant 1 angle or a negative quadrant 4 angle. So let's write out what we've got here. So if I think of inverse cosecant of x, the domain is the ratios, so that's not changing here, union 1 to infinity, but the range here is this restricted range, and the way we're going to say it is it's going to be negative pi over 2. And so let me actually on the graph show you what we're restricting it to here. So it's just like sine negative pi over 2 to pi over 2. The only issue is where it's undefined at 0, so I have to say negative pi over 2, oops, that should be bracketed, negative pi over 2 to 0, union 0 to pi over 2. Again, the reason for I had to split it up like that is it's not defined at 0. All right, if we now look at this graph of secant x, let's first do the domain and range. The domain is all reals except every pi over 2 plus k pi. And the range, same as the range of cosecant, negative infinity to -1, union 1 to infinity. And again, we want to keep it similar to cosine, or inverse cosine rather. And so we're going to restrict the domain from 0 to pi, so essentially quadrant 1 and quadrant 2 angles. And that will capture all the possible ratios. And let's see, and I should say that, the range is going on forever, so the box is just really boxing in the domain. Okay, so let's do y equals inverse secant, or arc secant of x. The domain will be the ratios negative infinity to -1, union 1 to infinity. And the range now will be from 0 to pi over 2, and I'm breaking up pi over 2 because it's undefined there, pi over 2 to pi. So again, just like inverse cosine, we're dealing with quadrant 1 and quadrant 2. Okay, the last one, cotangent. Well, inverse cotangent is the one that doesn't quite match up with its reciprocal function tangent, and we're going to see why in a second. Okay, but first let's talk about the normal cotangent graph. The domain is all reals except every k pi. And the range is all reals. I just want to double check. I have a feeling I may have said the range misspoke and said the range of capturing the range of secant of all real numbers. That's not true. I'm just capturing the range of going to infinity and negative infinity. So when I put that box around it, I'm just boxing the domain restriction, not the fact that the range goes to positive and negative infinity. Anyway, hopefully you get the picture there. Okay, so let's go back to cotangent. So for inverse cotangent, remember inverse tangent, we restricted it to negative pi over 2 to pi over 2, and we could do that here, but it's just much cleaner to restrict it from 0 to pi. So that's one that kind of just breaks the pattern of the others in matching up with their reciprocal functions. So if we talk about the inverse cotangent function, the domain is everything, and the range is going to be 0 to pi exclusive, because you can't, it's undefined at 0 and pi. So that's the one that, again, just doesn't follow its reciprocal in terms of the range. In terms of restricting the domain, which will then become the range of the inverse trig function. Okay, we're going to do a few examples. All right, so let's make room to do a few examples here. So first I want to point out that there is a difference between the following two problems. If I said solve, and problem A was the following: sine x equals 1/2, and problem B was inverse sine of 1/2 equals x. These are very different problems. Problem A has infinite solutions because there's infinite angles when I plug it into the sine function where I get 1/2. So to express that, you'd say pi over 6 plus 2k pi. That would give me all the quadrant 1 angles. And then I would say 5 pi over 6 plus 2k pi. That would give me all the quadrant 2 angles. And that's where sine's positive. So that would reflect, and again, where k is an integer. Now, the second one, it's saying you're applying the inverse sine function. So what is the inverse sine of 1/2? Inverse trig is a function, so there is only one answer, and that answer is based on what we used to restrict our sine function originally in order for it to have an inverse. So we would say that the inverse sine of 1/2 in this case, my x value is, again, only one answer. It's going to be a quadrant 1 answer. It's going to be pi over 6. So one solution versus infinite solutions. Okay, now what about something like this? Let's stick with sine for the time being. What if I said find the inverse sine of let's say 1.4. And since I don't have, actually a few things I want to say. Notice the inner function is regular sine. So that means 1.4 is an angle. It doesn't have a degree sign, so it must be in radians. And the outer function is inverse sine. Thus, the answer is going to be an angle. And we know that the sine function, sine composed with its inverse, a function composed with its inverse should undo each other. So the only thing you have to be careful of, though, is your answer better be in the range of inverse sine. So, but I know that 1.4 is a quadrant 1 angle, so this would be, and so this is going to be a positive ratio. So I'm doing inverse sine of a positive ratio. So yes, it will be a quadrant 1 angle. So it will completely undo each other. Now, compare that, however, to something like this. Inverse sine of, let's say, 2. Now, 2 radians is going to be in quadrant 2. So if this is 2 radians. So that also will be a positive ratio. So I'm going to want when I take the inverse sine of a positive ratio, I should get a quadrant 1 angle. Well, I can't just say 2 then, because that is not a quadrant 1 angle. That's out of the range of negative pi over 2 to pi over 2. So what is the quadrant 1 angle associated with 2? Well, let's go back to our picture here. The quadrant 1 angle is going to be this angle that's formed, which is going to be pi minus 2. So inverse sine of 2 then is going to be equal to pi minus 2. Let's try another. Let's say, kind of still sticking with this same theme here. What if I said inverse sine of 4? All right, well, let's see where 4 is. 4 is greater than pi, so we're going to be in quadrant 3. So this would be 4. So I know when we're in quadrant 3, the ratio is going to be negative. So I want a negative quadrant 4 angle, acute angle. Well, in order to find that, let's first find what this reference angle here is. And that's going to be equal to 4 minus pi. But that's the positive version of that angle. So in order to find a negative quadrant 4 angle, I'm going to say negative 4 minus pi. Or in other words, that equals pi minus 4. So you can see how you really have to think about these. In the final video, I'm going to get into kind of even some more tricky ones.